Hello and welcome back to Math with Mrs. Becker. This is College Calculus. Today we are looking at Chapter 0, Section 2, and really focusing on some important functions. Okay, so example 1, they really want to make sure that you are comfortable graphing linear equations. So remember, y equals mx plus b. That is the slope-intercept form of a linear equation. And that's what we're looking at here. They just have this in function notation. F of x can be interchanged with y equals. So these two things actually mean the same thing. And so what they want to make sure that you understand is how to graph a linear equation on a coordinate plane. When y is by itself, the number in front of x, this is called your slope. Your slope tells you your rise over your run. Now remember, the rise can go up or it can go down. If you have a positive slope, you will go upwards. If you have a negative slope, you will go downwards. Looking at the bottom, the run, you can only go to the right. So I always look at this kind of as thinking of your life. Your life, you're going to have ups and you're going to have downs, but you can only keep moving forward. You cannot go back in time. Okay, so that's what the number in front of x tells you. Now the value after x, that is called your y-intercept. And when you're graphing on a coordinate plane, that is your starting point. Okay, so for this particular equation, our slope is -2. I'm going to think of it as -2 over 1. Our y-intercept, because it's +5, is a +5. So if I go ahead and I graph this, okay, I'm just going to draw a coordinate plane here. Now your y-intercept, that is your starting point. Because it's +5 from the origin, I go up 1, 2, 3, 4, 5. That is my y-intercept. From geometry, recall that you only need 2 points to form a line. So to find my second point, I'm using the slope, which is -2. I put a 1 underneath it because now I can say I go down 2 because it's negative, and I go to the right 1. So down 2 over 1, there's your 2 points, connect your points, that is the line. So that's what example 1 is making sure you remember how to do. Okay, example 2, they want you to be able to identify intercepts. Now what intercepts are the location on a graph where your line would cross the x-axis, that would be called the x-intercept. Where that occurs, your y value is a 0. Because notice you would not be going upwards, you would not be going downwards. Your y-intercept is the location on the graph that touches the y-axis. At that location, the x value is 0 because you're not going to the right and you're not going to the left. So in order to do this, again, I want to change from function notation to y equals. So y equals 6x minus 18. If I want to find my 2 intercepts, to find the x-intercept, that means y equals 0. So I go to the equation, y is 0, 6x minus 18. I need to solve for x. So if I add 18 to the other side, I would have 18 equals 6x. To solve for x, I need to divide by 6. So x equals 18 divided by 6 is 3. So my intercept as an ordered pair, the x value is a 3 when the y value is a 0. So that means I go to the right 1, 2, 3, don't go up or down. That is called your x-intercept. You also have what's called a y-intercept. That occurs if your x value is 0. So again, I take this equation where the x is, I make that a 0. 6 times 0 is 0. 0 minus 18 is -18. Once you know your x and you know your y, you can write out your ordered pair. So 0, -18, that is your other intercept. So if I stay at 0, I'd have to go down 18 units to find the y-intercept. So that's how you do example number 2. Now, example number 3, they're going to start getting into application problems. And what that means is that you can read a real-life scenario and turn it into an equation. So let's do that. When renting a jet ski for the day, the cost is $22 per hour plus a $50 delivery pickup fee. Okay, so it's $22 every hour plus that one-time fee for delivery and pickup, and that's a straightforward $50. Write a linear function for the total cost, so they want it to be f of x, for the rental if the jet ski was used for X hours. They're just telling us that because they want us to use the variable X, which matches our function notation. This says we're writing a function where our variable is X. So we have $22 per hour, hours used as X, plus a $50 charge for delivery and pickup. That's it. Can you take a real-life scenario and write it as a linear function? Okay, next one. When a baseball is thrown at 85 miles per hour, is hit by a bat swung at X miles per hour, the ball travels 6x minus 40 feet. Okay, now obviously when you create a formula like this, there's a lot of components that go into that. So here are all the components. This formula assumes that the bat is 35 inches long, the bat weighs 32 ounces, and strikes a waist-high pitch so that the plane of the swing lies at 35 degrees from the horizontal. That's all of the information that they needed to know in order to create that equation. So kind of cool. How fast must the bat be swung for the ball to travel 350 feet? Okay, so it says when a baseball thrown at 85 miles per hour is hit by a bat swung, the ball travels this distance. So here's our equation. They want us to solve for X. How fast? X is miles per hour, so that's the speed. What would X be if it equals 350 feet? So 6X minus 40 equals 350. So what you did there is you took information and created an equation. You knew what it was equal to, so we're kind of working backwards to solve for X. Step 1, add 40 to each side. So 6X equals 390. Divide both sides by 6. 390 divided by 6, you would get 65. That is miles per hour. So the bat was swung at a speed of 65 miles per hour in order for the baseball to travel a total of 350 feet. Okay, here's another problem. Suppose that a cost-benefit function is given by f of x equals 50 times x over 105 minus x. And x can be anything in between 0 and 100 and including that 0 and 100, where x is the percentage. Now here's one of the odd times in mathematics where you will not change your percent in a problem to a decimal. The reason why is because they defined x as the percentage. So you leave it as it is, okay? So it says where x is the percentage of some pollutant being removed, and f of x is the associated cost in millions of dollars. Okay, so when we solve this, whatever the value is, that's how many millions of dollars it would cost for that particular percentage of pollutant to be removed. So it says if 60% of the pollutant has been removed, what is the added cost to remove another 10%. So in order to do this, we have to actually do two calculations. We want to know the added cost to remove an additional 10. So we need to figure out, okay, well, how much did it cost to remove 60%? An additional 10% would mean that we are removing 70%. The additional cost would have to be found by subtracting the two. Okay, so in order to do this, I'm going to go ahead and put 60 in for x. So 50 times 60 over 105 minus 60. Again, the reason why I kept it as 60 and not 0.6 is because in the problem, they told us x is the percentage. So you keep it exactly how it is. 50 times 60 is 3,000. 105 minus 60 is 45. So if I take 3,000 divided by 45, I get 66 point, and it's 6 repeating, so I'm going to go 667. And again, that's an approximate answer. So 66.667, that is millions of dollars. That's how much it costs to remove 60% of a pollutant from, maybe it was a pond or a lake or the air in a certain park, okay? They're saying, well, what would the additional cost be if you went another 10%? That means instead of 60, let's go to 70. So 50 times 70, 105 minus 70. So 50 times 70, we have 3,500. 105 minus 70, we have 35. So if I take 3,500 and I divide it by 35, we get $100 million for you Austin Powers fans. Okay, so that's not what the question was asking. The question says, what is the added cost? So we need to subtract the two. So 100 minus 66.667, and the reason why I'm putting approximate is because I rounded that first value. So 100 minus 66.667, it would be approximately an additional $33.33 million. So at that point, they need to look and say, okay, we've already removed 60% of the pollutant. It's going to cost us another $33.33 million if we want to remove 70%. Do we want to spend the money to do that? Okay, I kind of like these questions, okay? It says, how does this compare to the cost of removing the final 10%? That means you are removing every single stitch of pollutant. So the final 10%, what that means is that we would be going from 90% to 100%, because that would be the final 10. So 90 to 100. So if I take 50 times 90, 105 minus 90. 50 times 90, we got 4,500. 105 minus 90, we've got 15. So now if I go ahead and divide them, 4,500 divided by 15, this is 300. And again, this is millions of dollars. So if you remove 90% of a pollutant, it's going to cost you $300 million. Well, they want to know what is the additional cost for removing the final 10%. Well, if you're at 90, we might as well remove it all, right? So 50 times 100, 105 minus 100. 50 times 100, you guys, we're up to 5,000 here. 105 minus 100 is 5. So we have 1,000 million, or that's the same as 1 billion. I'm keeping it in million because I'm not done, okay? So, but here's the crazy thing. If you are removing 100% of a pollutant for whatever this area is that they're talking about, it's going to cost you $1 billion. That's insane, okay? They want you to compare going from 60% to 70 and 90% to 100. So I need to subtract. So if I take 100 million, or 1,000 million, sorry, which is 1 billion, and I subtract the 300, what we have is $700 million. So what they want you to realize that is as you remove more and more of a pollutant, the cost gets higher and higher and higher. This is still just 10% difference. You're going from 90 to 100, but it's $700 million more because you're getting close to having no pollution at all. Where at the beginning of the problem, when we went from 60 to 70, it was only $33.3 million. So it's just kind of looking at how some real life examples work. It's not just that it's 10%. The more you remove, the more spendy the process will get. So there's a fun example. Oh, sad, we're almost done. Okay. Turn the note page over. We are looking at quadratic functions. Remember, a quadratic function is ax squared plus bx plus c. That's what a quadratic is. That's the format that we always had it in before we use the quadratic formula. prior to completing the square, factoring, all of those different things, okay? So they're going to give us formats that kind of look a little funky. They want us to determine what is the value of A, B, and C. Well, one thing that we want to make sure that we remember, if you have a polynomial on the top of a monomial, what you are allowed to do is separate this out into multiple fractions. So what that means is I can have y equals, the number is 2 over 3, so I'd have 2/3 x squared, minus, because there's a minus sign. Now 7 goes over 3, that's x, plus, because it's a plus sign. 9 over 3 is 3. These two things are equivalent. It's just another way of writing it. So now when I have it this way, it's easy. A is the number in front of your squared term, 2/3. B is the number in front of x, -7/3. C is the constant at the end, it's a 3. Okay, now what happens in the next one, they're kind of trying to throw you off by having pi and square roots and whatnot. The main thing is this problem is not in standard form. You want to rewrite it. Remember, your squared term comes first. Anytime you have a minus sign, it's always tagged with whatever's behind it. So this would be -1/2 x squared. Now this term has a single x, so it's a positive square root of 3 times x plus pi. Remember, pi is a number. It's 3.14159, and you keep going and going. This is not a variable. It is a number. So my A, what is the number in front of x squared? Well, it's -1/2. B, the number in front of x, square root of 3. C, the number at the end, is pi. So just reminding you what quadratic functions, what that basic equation looks like, and making sure you still know how to identify what is A, what is B, what is C. Okay, last idea for the day is just a reminder of how piecewise functions work. Now remember, piecewise functions, they state a different domain for each piece. And so when we go ahead and we graph this, you're going to graph this piece and this piece on the same grid. But when we do our XY table, we have to stay within this domain. And you always include the endpoints. So here I would go -1, 0, 1. It includes the -1. So when I graph, that would be a filled in circle. It includes the +1. So when I graph, that includes the circle. So if I go ahead and I do this, and if you want to use your calculator, great. I figure this is a good time to remind you how to use the fraction key on the calculator. If I go 5 over 2, remember this fraction bar, A, B/C, open a parenthesis, we're going to multiply it by -1 minus fraction bar 1 over 2. So I would get a -3. Up arrow, another fun thing just to review because we're at a new school year here. I can delete the negative. I want to put in a 0. If I put in a 0, my y value is -1/2. Now I just want to up arrow and I want to change that x value from a 0 to a 1. I get a 2. So that is one piece. This is a linear function. I know that because I have a single x. When I go to graph this, when I connect it, I need to keep in mind what kind of function it is. I'm going to go 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So here I go to the left one down, 1, 2, 3. This is a filled in circle because it does include that endpoint. 0 is at -1/2. 1 is at 2, and again, it's a filled in circle. So that is the first piece of my piecewise function. Okay, now I have to graph the second piece. So again, you are making an XY table. You have to include the starting point. Even though it's not included, I have to include 1. It's just going to be an open circle. This again is a linear function. I'm going to go ahead and put in values that are greater than 1. So I have to start with 1, show that it's an open circle. A couple values greater are 2 and 3. Again, calculator, if I go 1 over 2, that's my fraction of 1/2. Open a parenthesis, we're putting in a 1 minus 2. I get -1.5. If I up arrow, I can just change that 1 into a 2, and you don't have to retype the whole thing. This is -1. If I up arrow, this time I want it to be a 3. So I get -1/2. So again, this is a linear function because it has a single x. I want to graph it on the same grid. I'm going to use a different color here. If I go to the right 1, I go down 1.5, open circle. To the right 2, down 1. To the right 3, down 1/2. Now, this was bounded. What that means is that I have two distinct endpoints. This says x is greater than. So this is an open circle. This line continues to the values to the right. So that is what a piecewise function is. Let's do one more to make sure we've got it, and then we are done with 0.2, you guys. Again, I have different pieces with different domains. So the first one, linear function, it's going to be a line because it's a single x. When I make my xy table, I need to include the 0 and 2. So I will say 0, 1, 2. The 0 is included, filled in circle. The 2 is not included, open circle. If I fill a 0 in, 2 times 0 is 0. 0 minus 1 is -1. If I fill a 1 in, 2 times 1 is 2. 2 minus 1 is 1. If I fill a 2 in, 2 times 2 is 4. 4 minus 1 is 3. That is my first piece. This one, again, is what they call bounded. I have two endpoints, so there are no arrows. 0, -1, filled in circle. 1, 1 is a point. 2, 3 is an open circle. There is my first piece. When I go to do the next piece, this time I have a constant. What that means is that for each value of this domain, the y value is going to maintain its value of 3. 2, 3. The 2 is included, it's a filled in circle. The 3 is included, it's a filled in circle. My value is a constant. I'm going to go to the right 2, up 1, 2, 3. Notice that they connect. Sometimes your piecewise functions will connect, sometimes they will not. 3, 3. If I go the right 1, 2, 3, and I go up 3, there is another point. This again is bounded. It has a starting point and an ending point. The last piece, again, it's a linear function because it's a single x in the equation. I need to include the 3, even though it is not included, it's technically the starting point. So I just need to make sure that I have an open circle at that location. Then I need to pick x values that are greater. So I will go 4 and 5. 3 plus 2 is 5. 4 plus 2 is 6. 5 plus 2 is 7. Now this one is not bounded. This says x is greater than, so I will have an arrow going to the right at the end of this. So 1, 2, 3, 4, 5. I just have to extend this a little. 1, 2, 3, 4, 5, 6, 7. Okay. When I graph this, I go to the right 1, 2, 3, go up 1, 2, 3, 4, 5, open circle. To the right 4, up 6. To the right 5, up 7. X is greater than, so it continues. That, my friends, was 0.2. Here is the suggested assignment. These questions will help further your understanding. I hope you had a great day, and I will catch you later.